data set that is used in the Navarro textbook. It's 18 participants in 3 groups, and there's a drug factor, placebo, and then 2 drugs, anti-C3 and joyzepam. Those aren't real drugs, by the way. And then there's the second factor called therapy, but we're going to get rid of that today because we're only going to look at a single factor in NOVA. And then the dependent variable is some measure of how much your mood improved. So 6 people get placebo, 6 people get anti-C3, 6 people get joyzepam. Different people in each drug group, so it's between subjects and NOVA. Now you'll see in, remember when we looked at data frames or templates, we saw just below the title was this thing in angular brackets that defines the variable type. So our dependent variable is DBL, which is a double precision floating point value. In other words, just a number, a real number. And for the 2 factors, the data type is FCT, which stands for factor. And for doing ANOVA in R, it's critical that your variable that defines the level of each factor is actually coded in R as a factor, FCT. Sometimes when you load in data, like from a CSV file, it will encode alphanumeric, things like that, as a string. And I think, unfortunately, even if you pass that data to an ANOVA, it won't complain. It won't say, oh, you're giving me strings, I want factors. It will just do something, and probably the wrong thing. So you have to always make sure that the levels of that the variable that encodes the level of your factor is being coded as a factor. And there's a command called factor where you just you convert, for example, strings into a factor. Okay, so for now, let's ignore the therapy variable. And in fact, we can just get rid of it using select minus therapy. We'll chop off therapy. So we've got drug and we've got mood gain. Before we run the ANOVA, we can just look at some summary statistics. If we want to know the number of participants in each group, we can use this xtabs command. Squiggly drug, common clinical trial, and we get 6 in each group. If we want to compute the mean of each group, there's a handy command called aggregate, where we give it, kind of like a linear model, we give it a formula. Mood gain, squiggly drug, comma, clinical trial, comma, mean. So it applies the mean command to each level of drug. And we get the means of our groups. We can also get the standard deviation of each group. So aggregate is a handy command to get means and anything you want actually. We can also do the same thing by using our dplyr tidyverse skills that we learned about earlier. We could say clinical trial, and then pipe it to group by drug, and then pipe it to summarize, and then n equals n, mean equals mean, SD equals SD, and we can get the table with the number in each group, the mean, and the standard deviation. So I just wanted to show you 2 ways of doing the same kind of thing, just to get an initial impression of what the means are and what the standard deviations are. Because the standard deviations are a measure of variability within each group. We can also generate a plot. There's a library called gplots, which has a handy function called plot means, where again you can give it a formula. Mood gain varies with drug. That means the levels of drug will be on the bottom and mood gain will be on the top. And it'll give you a plot of the means, and you can show you the number in each group, and it'll label everything nicely. And the blue lines here are the 95% confidence limits. But you can ask for different things if you want, like a standard error. But of course, we can use ggplot. And I was looking at this morning, and I thought, oh man, that's okay. And then you go to the ggplot version, and it's like, like that's not a good advertisement for using ggplot. It's a lot more code. On the other hand, I kind of like that plot better. You'll see this flavor, this style of plot more and more now in scientific articles. which is a good thing. You know, the convention for many decades was to show means and then error bars. But recently, people have clued into the fact that, you know, means and error bars can actually hide some information, like the skewness of a distribution, for example, or outliers. So the convention nowadays is to plot means and error bars, and then overlaid or behind, plot the raw data points as well. So you actually see the raw data, and you see the means and the error bars. And so do that in ggplot. It's not such a big deal. Clinical trial type to group by drug, type to summarize. Then you compute standard deviation and standard error, 95% confidence limit. And that gives you a new tibble. And you pipe that directly into a ggplot command, where you put on some error bars, you put on some points. For the means, you use geom jitter to jitter the raw data, and then you put some labels on there. That's not such a bad thing, actually. And it's infinitely customizable, which is nice. So you can adapt that kind of code for your homeworks, for example. That would be totally fine. Okay, so we have these three groups, a placebo and two drug groups. So are the differences between these groupings real, or are they due to random chance? And when I say real, what I really mean is, are the differences between groups here a faithful representation of the means of the underlying population from which those groups were sampled? Or are they not? In other words, were these three groups sampled from populations that actually had means that were that different? Or is the null hypothesis true, and those three groups were sampled from one population with one mean, and we're just unlucky, we just happened to pick a bunch of people for the joys of hand drug that happened to be on that side of the normal distribution. So how likely is it that could happen? The omnibus test, like we saw before, gives an overall measure of the relative difference of the difference between means and the differences within the group. Here's how you run the ANOVA in R. It's really simple. You give it some output object, I'm going to call it my.ANOVA, equals AOV. Why did they not call it ANOVA? Like literally ANOVA? Well, there is a function called ANOVA, but it does something tiny bit different. So we're going to use AOV, and just like a linear regression, you give it an equation. New gain, squiggly drug. New gain varies with drug, comma, data equals clin.trial, and it puts the result of the ANOVA in an object, just like LM puts the results of the linear regression into an object, a model object. And then when you do summary of that object, you get this ANOVA output table, where each row is a source of variability due to the drug, and residuals is the leftover variability. And then you get the columns or the different quantities in the ANOVA table. Degrees of freedom, sum of squares, mean squares, the F value, and the P value. So we get a p-value that's very small, 0.0000865, so way below 0.05, way below 0.01. So we would reject the null hypothesis that these drug groups were sampled from one population with one mean, or populations with the same mean. And we would implicitly accept the alternate hypothesis, which is, well, if those differences between groups aren't due to random chance, what are they due to? Well, they must be due to the drug, because the drug is the only thing that happened to those people that are different, depending on what group they're in. They were randomly assigned to receive placebo or one of the two drugs. And so the only possible explanation for these differences is what drug they got. That's what we were concluding. Okay, so getting to the ANOVA table actually is really easy. It looks just like a linear model in regression, in fact. The output is a bit different, but the things we're interested in are the F value, and you can see it's big, 18. So the between groups variance was 18 times bigger than the within group variance. And the p-value. Questions about that? Oh, yes, sorry.
Does it not show the within groups in the output? Or is that the residuals?
The within, yeah, the within, oh, I see. Yeah, that's the residuals.
Okay.
Yeah, it's R of the residuals. And so why are they called residuals? The idea is that it's the variance that's left over that's unexplained. So we're trying to explain the variance in terms of the difference between groups. That's the part we're trying to explain. And anything we can't explain is basically represented in the leftover. So P is less than 0.05, we reject the null. Now, what is different from what? We don't know yet, right? Our omnibus test tells us something's happened here. These groups were not taken from populations with the same mean. The chance of getting differences between groups that big is really low. Okay, so which drug works? Well, I mean, by looking at it, we probably have a good idea that that's the one responsible for driving the effect. But that was also a little bit different. So, you know, what's different from what? That's what we use follow-up tests to assess, and we're going to talk about that next time. And an issue of great importance, like I said, is type 1 error rate. The preview is if we were just to get an omnibus test that's significant and then say, okay, great, I'm going to test whether those two are the same, whether those two are the same, and whether those two are the same. I'm going to do 3 tests. And I'm going to do each test with an alpha level of 0.05. Your actual error rate over those family of tests is going to be much bigger than 0.05. You're actually going to make closer to 15% cycle errors, even though each individual test you think you're making only 5% cycle errors. So by not correcting, basically, you're performing much more liberal tests than you ought to be, than you think you are. But we'll talk about that next time. So what about assumptions of ANOVA? The important ones are normality, and we can test normality on the residuals, just like in regression. Homogeneity of variance across groups. That's kind of like homoskedasticity in regression, but now it's called homogeneity of variance. The assumption here is that the variance of the populations from which each group was sampled are equal. So it's an assumption about the populations. Now we can't test the populations, all we have is the samples. So we test that assumption based on our samples. And independence of observations. Each observation has to be independent from each other. And just like regression, there's no numerical test for that. That's a more conceptual thing that you have to think about how you ran your experiment to be able to verify. So the residuals are assumed to be normally distributed. We can plot a histogram of the residuals and just look at them. We can also produce a QQ plot, just like in regression. And there's a hypothesis test called Shapiro loop that we can do. So for the data we just saw, if I plot the histogram of the residuals, it's not a lot of data, so it's chunky histogram, but it's kind of like, yeah, see in the dish. I can generate a QQ plot using these 2 commands by just feeding it the my.ANOVA model object. And if everything's good, then these points should fall along that straight line. And for that one, I would say, yeah, it's okay. It's probably fine. It's a little wiggly, but it's not much data. So it's probably fine. Usually when normality is violated, you see this pattern where the tails are departing from the line. It might come up like that, and then go down like that. It would look more like a sigmoid. So if the tails are okay and the middle is okay, it's probably fine. You can do a Shapiro dot test on the residuals of the model object, just like regression. And just like regression, the null hypothesis is that the samples came from a population with a normal distribution. So the null hypothesis is the one that means everything is okay. So when you get a p-value for the Shapiro dot test, you want it to be greater than 0.05. This one's way bigger than 0.05, which means we don't reject the null, which is the assumption that we want to be true. So we're good. Normality assumption is not violated. Yeah.
So with residuals, I understand where we get them from for linear
Regression.
model, but how do we get them from this?
Yeah, so the question was about residuals, and you said that you understand how we get residuals from a linear model. It's those vertical distances between each data point and the line. But how do we get them for ANOVA? I'll show you a plot at the end of the slides that helps answer that, but the short answer is, well, I'll show you now. It's not that far off, and then we'll look at it again. That's the equivalent sort of graphical representation of the linear model in ANOVA. Instead of modeling all the data points with a single line that sort of slopes according to an independent variable, now we just have a bunch of data points in group 1, a bunch of data points in group 2, a bunch of data points in group 3. And our model, our ANOVA model of those data is that each group has its own mean value. And any departure of an observation from that mean value within each group is the residual. So it's still a vertical distance between each data point and the average of that data point's group, basically. So that's the ANOVA model that assumes that each group is sampled from a population with its own mean. And that's the null hypothesis in ANOVA. No, there's only one population mean. And all the data points come from that one population with that one mean. And any deviation is just random chance. So which explains the data better? That model with 3 parameters that we have to estimate, one mean for each population under the alternate hypothesis, or that, where there's one parameters to estimate, one population mean. This model will have smaller residuals, right? That model will have bigger residuals. But this model has more parameters. This model has 3 parameters, and that model only has 1. So again, just like regression, we want to multiple regression, we trade off the goodness of fit of the model with how many parameters we have to assume and estimate of the model. Yeah.
So we just kind of choose at our own discretion which one we want more?
No, that's what the F ratio indirectly assesses.
So you would do like 2 F ratios for like one with the restricted model and one with the full model?
Yeah, just like in multiple regression, we can develop a restricted model and a full model in ANOVA, and each one will have an F ratio, and we can test them. Yeah. We're not going to do that kind of thing today, but we can do that, yeah.
It's like they have like the AIC and stuff like that too.
That's right, yeah, they also would have an AIC. Yeah, you're getting a little bit ahead. So that's where we're headed eventually, and where you'll be headed next in your course next year. So just to drive this home even more, you took us a bit off course, but it's good. So with the, that would be the restricted model, right? With 1 parameter to estimate and pretty large residuals. That's a full model with 3 parameters and smaller residuals. Forget that this is 3 groups for a moment. Like, what if we had another model, and instead of having 3 parameters, we had 15 parameters, right? We had 1 parameter for each data point. What if I just drew a horizontal line through each data point and said, I have a new supermodel. It has 15 parameters. And you know what? The residuals are 0. It's a perfect model. Good news, I have a model that fits the data perfectly. Like literally perfectly. The error is 0.0. So why not do that? Like, what's the downside of doing that? It's a bit of an extreme example, but why not? Yeah.
I guess it doesn't really tell you anything about the overall model because it's so like focused on the time point.
Yeah, you said that it doesn't really tell you anything about the overall model or concept because it's so finely detailed. and I think you're right. What it's getting to is the idea that if we had one parameter for every participant, then basically what we would be saying is everyone is different. Everyone is their own population. And there's no generalizing of anything, right? There's no sort of population where everyone is the same, everyone has the same mood or everyone has the same memory, plus or minus some variability. We would be saying literally everyone is their own universe, and there's no generalizability. So that's not the kind of model we want to develop, right? We want to, in science, we want to study phenomena that are common to people or common to organisms or common to chemical elements. There's no generalizability that we can't really learn anything. So conceptually, that's a good reason. What about mathematically or statistically? What would be the downside of a model with zero error?
This has to do with the degree of freedom that you mentioned a few weeks ago.
Yeah, it does have to do with degrees of freedom. Yeah, so if we had as many parameters as data points, how many degrees of freedom will be left over? Zero. We wouldn't have any left over. And remember, degrees of freedom left over appears in the denominator of one of those ratios. And so can we divide by zero? Is that allowed? No. So at the very least, if we tried to compute that model, R would complain, divide by zero error. Right? So like mathematically, the model is not even properly defined, but we have the same number of parameters as data points. Okay, that was a bit of a tangent, but I think it was good. It kind of drives home this concept of model complexity versus model fit, and it kind of drives home the rationale for wanting fewer parameters rather than more. And it also illustrates the idea that an ANOVA is, it's a lot like a linear regression model like we saw before, both in terms of the trade-off between parameters and model fit, but also in terms of residuals and how they're defined. So what was in between? What do we need to talk about? Maybe not much. We talked about homogeneity of variance. No, we were just talking about normality. The Shapiro test, right. This shouldn't take long. If the normality assumption is violated, we can still do an ANOVA, but we should use a non-parametric version of ANOVA called a Kruskal-Wallis test. It works on the ranks of the data, not the actual values of the data, but it's the same concept as an ANOVA. The Navarro chapter will give you more details about how it works. But basically, you call Kruskal.test and you give it the same squiggly formula, and it gives you a chi-squared statistic instead of an F, and it gives you a p-value, and it's the p-value you're interested in. Just like a regular ANOVA, it's p less than 0.5 and rejected. So you can still run an ANOVA-like test when normality is violated. You just use the Kruskal-Wallis test. Homogeneity of variance. The assumption is that the variance, or standard deviation, if you like, of the populations from which the samples are drawn are equal. And we can test that using our sample data, where the assumption is that the residuals have the same variance across groups. The test is called the Levine test, and it lives in this package called CAR. So you have the library CAR, and if you don't have it installed, you might need to install packages CAR once. And then you say Levine test, and you give it the formula, and you get a F value and a P value. And just like the normality test, you want the P value to be greater than 0.05, because the null hypothesis is that everything's okay. So that's okay here. We don't reject that null hypothesis. Homogeneity of variance is not violated. We're okay. If it is violated, then we still have an out. Instead of our regular ANOVA test, we use what's called a Welch one-way test. And in R, we can do that with one-way dot test. And you can see the chapter for details about that. It's basically a version of an ANOVA. Yeah, here it is. You still get an F, and you still get a p-value, but you can see what's a bit weird. You get numerator degrees of freedom 2, which is the same as our ANOVA, but now the denominator degrees of freedom is, what, 9.4932? How can degrees of freedom have a decimal point? What the Welch test does is it adjusts the denominator degrees of freedom of the ANOVA. It reduces it, in proportion to how much of a violation exists in homogeneity of variance. It makes the test more conservative the more there is a violation of homogeneity of variance. And it's sort of a continuous adjustment, which is kind of nice. In fact, some statisticians say, instead of testing homogeneity of variance and then either using an ANOVA or using a Welch test, we should just always use the Welch test. Because if homogeneity of variance is not violated, then the Welch test isn't going to do much of an adjustment. It's fine. And if it's violated a little bit, you'll have a little bit of an adjustment, which is appropriate. So that's just something I'll throw out there. In the case of homeworks and an exam, I'll ask you specifically which one to do. Independence of observations, there's no test for that. Like I said, it's conceptual. Some basic things, you should always make sure to do random sampling and random assignment. If those are not happening, then you probably don't really have independence. A clear violation would be if you have repeated measures within each group, which means that a participant contributes a score to more than one level. Like if people have the placebo and then the same people have the drug, and the same people have the other drug. That's no longer independence of observations. That's no longer between groups ANOVA. That's a within groups ANOVA, which you can do, but it's just a different procedure. Yeah, so like we saw with those graphs, ANOVA is a linear model of your data. Each observation, the ith observation in the jth group is equal to mu sub j plus random noise, random variability. Mu sub j means that it's the mean of the jth group. That's the full model of ANOVA. Each group has its own population mean, mu sub j. Right? Each group is sampled from a population with its own mean. That's the alternate hypothesis. The null hypothesis is that no, there's only one mean. There's not mu sub j, one for each group. There's just one mean. And everything else is in this error term. Everything else that's not that mean is random noise, it's random error. So that's the null hypothesis. So null hypothesis is the restricted model. Alternate hypothesis is the so-called full model. So you can think of ANOVA as comparing two linear models of the data. Just like we had multiple regression. Do I need x1 and x2 in there or just x1? It's the same kind of concept. You've got two linear models of the data. The only difference is that this model estimates a different mean for each group, and that model only estimates one grand mean. This model will fit better, but use more parameters. This model will fit less well, but it only needs one parameter. So in an indirect way, when you run the f-test on the ANOVA, when you get that f value or the p value, that's kind of what the ANOVA is assessing. Do I really need three parameters to explain these data? Or can I just use one? That's an equivalent question to, are these three groups sampled from populations with different means? Or just from one population with one mean? It's the same conceptual question as asking, do I need three parameters to model these data or just one? And there's a direct correspondence between those two ways of thinking about the model. And once you start thinking about ANOVA and all of its flavors in that second way, in terms of just like, I want to model my data, how many parameters do I need? It's a really cool way of thinking about things because it becomes really flexible. We don't need to look at that again. Full model, 3 parameters. Restricted model, 1 parameter, and it's a trade-off. And 15 parameters is the silly model with perfect model fit, but no generalizability and not possible to actually compute the error. Yeah, we talked about this already. Is it worth it to estimate 3 parameters instead of 1? Just like regression, you can think of this in terms of moving 2 degrees of freedom from here up to there. The increase had better be worth it. You can look at that later. So let's look at our running tally of models. That's a model with nothing in it, just randomness. The average is 0, and everything that's not 0 is just random error. That's a model where we estimate just an intercept, just a mean. That would be like the restricted model in an ANOVA. All the data come from one population with a mean, and then everything that's not that mean is just random variability. That's our linear regression with one predictor, an intercept and a slope. That's our multiple regression, where in the figure is a plane in 2D. We have x1 and x2. And now we've added to that, now we have ANOVA, where we have a full model with 3 predictors or a restricted model with just 1. And so, as we go on with different flavors of ANOVA, we're going to look at, I think is it next, after the next lecture, is it ANCOVA? Yeah, after we talk about follow-up tests in March, we'll look at analysis of covariance and COVA. And the C, the covariance, refers to the fact that we're going to have a model now that's really a combination of regression and ANOVA. We're going to have a model with a categorical variable in it, like ANOVA, but also a continuous variable, like regression, which is kind of cool. And it allows us to do some pretty important things. So we'll see that. And then after we look at ANCOVA, we'll look at factorial ANOVA, where we have more than one factor, like drug and therapy treatment. And then at the very end, we'll talk about repeated measures ANOVA, where we have multiple observations from each participant. And then what we're not talking about in this course is a mixed ANOVA, where you have some repeated, some between. But I'll give you resources to look at that later if you want. It's not really conceptually much different. The complexity in mixed ANOVA comes with estimating all those terms of the ANOVA table. And it's a real nuisance. It's kind of ugly. But the concepts are the same. Okay, that's all. Any final questions before we wrap up? Yes.
Earlier when you were talking about the Welch test,
Welch
you said
test.
that reduces the denominator df.
Yeah.
How does that make it more conservative? Wouldn't that increase the x factor?
Yeah, so the question was about the Welch test, and I had said it reduces the denominator degrees of freedom, and how does that make it more conservative? So let's look at that. So the Welch version, the denominator degrees of freedom is 9.4. And in the regular version, it is 15. Oh no, that's the mean test. Where's our ANOVA? Yeah, in our regular ANOVA it's 15. So it goes down from 15 to 9 point something. How does that make it more conservative? Well, there's a dumb answer I can give you, which is just that, well, when you either look up the p-value in the table or you compute it, it just does. The p-value is higher, so it makes it more conservative. Think about it conceptually. What would it mean if the variances were unequal? What would it mean about how certain you can be about those sample estimates being true reflection of the population estimates. Like, let's say you had two groups with the same variance and one group that had much bigger variance than the others, but its mean was also different. Versus the same scenario with equal variance.
You might expect they're even more likely to be different populations because.
That's right. Yeah, if the variance is bigger than the other variances, then it's probably a larger chance that you can get a difference between means due to just sampling error if the population from which you're sampling has bigger variability. Right? So it would reduce your certainty that the difference between means is kind of an actual difference between population means.
But does it increase the F-stat?
Oh, I see, numerically.
Yeah.
Yeah, we have to sort of look at the numbers. So the denominator degrees of freedom is this one here, DFW. And so that, let's work through it. If that gets smaller, then this thing gets bigger, right? And if that gets bigger, then this gets smaller.
Oh, because it actually decreases.
So it decreases F. Yeah, good, that was worth going through. So did everyone see that? The Welch test reduces the degrees of freedom within, which means mean squared within gets bigger, because the thing on the bottom is smaller. And if mean squared within gets bigger, it's on the bottom of the F. So if that gets bigger, then this whole thing gets smaller. So the more homogeneity of variance is violated, the more the Welch test dials down F. So basically, without the adjustment, you might have a big F and say, oh, maybe there's a real difference. But if the variances are unequal, the Welch test kind of dials down that F and says, hold on, you can't be so sure because your variances are different. You're going to squash the F down a bit.